Hi, how are y'all doing today? Today, I'm going to present a little bit about my research. Uh, Title of the topic is Cross Facility Reliable Deep Learning for Beef Marbling Assessment. And able to do that, we're going to use a little technology called unsupervised domain adaptation so that we can have practical automated grading. And then my name's Sam Vincent. I'm from the University. But in brief, as an initial summary, um, the main problem is that a model trained at one plant loses accuracy significantly when scored at another. And that's a real barrier for industry-wide deployment. And then the approach is we're going to use a new technology called unsupervised domain adaptation using a Resident 50 backbone to learn from unlabeled images at a new facility so that you don't need to have a USDA grader at a new facility. And then the result is that cross-facility error dropped about 12.9% with real-time processing speed. Real-time processing speed, so that we can have practical and scalable grading. But a little bit about my background. Grew up in Van Buren, Arkansas. Drive up 15 minutes to my grandparents' farm in Silent Springs. Bunch of cattle, 160 acres. So this project's definitely more personal for me. Spent a lot of time, just running around the field, looking at the cows, shooting BB guns, playing in the river. Did whatever kids did back in the day before smartphones. And then my mom, she grew up competing in all the 4-H competitions, raising a steer, ended up winning it one year out in Benton County. And my grandfather was never like a professional cattle farmer. He would always just take it down to Silent Springs meat processing plant, get some ground beef, or sell it at the Benton County sale barn. But my engineering background turned beef quality and beef grading into a question. If we were to apply a model to grade beef sufficiently, can we train it in one facility and have it reliable across the country? Because in the United States, the beef industry is very big, huge. It's worth about $140 billion each year. For scale, the two biggest companies in the world, Amazon and Walmart, bring in about $700 billion a year. $140 billion a year, that's a lot of money. And in order to sell, stay commercially, you need to have a USDA Prime or some sort of USDA grade on the package. And that's broken into USDA Prime, Choice, and Select. And those are determined solely based off of the white marbling that you see on the packages. So, or on the meat. And the more white marbling you have, the more fat you have, the richer it is. So you look moderately abundant, slightly abundant, it's USDA Prime. Moderate and modest, that's USDA Choice. And then small and slight, that's USDA Select. Now, I don't know about you guys, but we grilled some sirloin steak at the Vincent household last weekend for the 4th of July. It was pretty good. We got some USDA Prime sirloin steak. Pretty great. But marbling, at the end of the day, influences USDA quality grade, product value, and consumer expectations. And scoring needs to be accurate and consistent at an industrial scale. So the deployment problem is that conventional CNNs, conventional models, learn best from labeled images. Images that you know exactly what's going on. And it works best when the images look similar. Similar background, similar setup. And then also it's a fine-tuned regression. So we're all engineers here. We've all calibrated a pump or a sensor, but you change the environment of that pump, change the pipes, change the fittings, your calibration curve's wrong. The same thing for a sensor. Take it outside and it's completely, you need to recalibrate it. And the same problem applies for these convolutional neural networks. If you bring it to a new facility, it's going to have a lot of trouble adapting, then you need to retrain it. And then you lose that initial calibration curve. In a new facility, there's a lot of new issues. there's lighting changes, there's changes in camera calibration, there's changes in how you orient the carcass, and all of those types of things. So when it comes to cross deployment, it's the same task, but transferability is not guaranteed. So for main objectives, we have 3 goals here, and we're going to break down every single one of them. So we're going to measure performance degradation for traditional convolutional neural networks under same facility and cross-facility conditions, so that we know that it's not ideal. And then we're going to build a domain adaptation model so we can fix the problem. And then we're going to evaluate whether or not it's actually practical to have. So let's talk about domain adaptation. And this is the most complicated part of the presentation, but I'm going to try to break it down as simply as possible for you. And I'll tell you a story. So I studied abroad in Mexico 2 summers ago, and I lived with a host mom who did not speak English at all. So in order to communicate with her, my Spanish had to get a lot better to be able to express the same ideas so that we can share experiences. I could talk about my day, I could talk about how great her food was. And the same thing applies here. It trains based off of like a source facility where we had the USDA grades, and then we start to show it information from other facilities that doesn't have information. So eventually, over time, it begins to learn the other language of the other facilities. And then as a result of that, all the variation in different facilities, different camera angles, different lighting conditions became more generalized. And it began to start to focus on the white marbling, the fat particles, because that is what determines the USDA grade. That's what determines the richness. And it does this by using a domain discriminator. It knows whether or not it's originally from the original facility. And if it's not from the original facility, it applies a complicated math function to be able to translate it. And as a result of this, it spits out a grade that is pretty similar to what you would see from a USDA grader. And then from a data set perspective, we had about 1,758 images. We had 4 processing plants. We had 7 collection dates, and we had 3 USDA graders per image. And there were basically 3 USDA scores from 3 different graders. I would take the average of those 3, and then that's what I ended up putting into the model. So from the source training, which was the information that we knew, I used Plant A for the source training because Plant A was had our most number of images. So I used the 3rd date for training, and I used the 1st date for validation. And then for the target adaptation, I used the rest of the plants without scores. And then for the evaluation, whenever I tested at the end to make sure that it worked, I used a facility that I used a set that the model had never seen before, which is the 2nd date of Plant A. And then I use the cross facility B, C, and D with labels in order to evaluate it. And reusing the same stuff for target and evaluation is known as a transductive experiment. If we had more data, I would have been able to organize it to completely withhold other stuff. And then from a human grading baseline, the USDA graders range from about 270 to 900. But the standard deviation was very tight. There wasn't much variation between grader to grader. The mean per image standard deviation was about 20 marbling units. So pretty good. And we realized the goal from this is not necessarily to be better than humans, but to be able to reallocate the humans to higher value work. So from a training and evaluation perspective, we're going to go through this at a high level, but we use ResNet 50, we use PyTorch 2.6. We used a very fancy GPU, courtesy of the Arkansas High Performing Computing Center, and for training we had 200 epochs with a batch size of 10 with an atom optimizer. Then we evaluated mean absolute error, and then we did a bunch of statistical tests, two-tailed t-tests, and we also did some hyperparameter tuning to get the best result. And we trained it, we evaluated it, and then we validated it. But now let's talk about how the conventional convolutional neural networks don't really get the job done. So the same drop-off appears in almost every architecture we tested. We tested 5 independent convolutional neural network models, and the average change ranged from about 10 to 20 for each model. And then from a domain adaptation, and then also for AlexNet didn't perform exactly as we anticipated. And the difference between cross-facility wasn't really that large, but the same facility, the ground truth didn't necessarily perform very well at all. And then, but if we zoom in on the domain adaptation experiment, the cross-facility generalization is a lot better. There's almost a 7-point gap, 12% reduction with a statistical significance of p-value less than 0.05, and there's almost no trade-off when it comes to same facility mean absolute error. In fact, it actually ends up performing a little better. And then the gap is real. Both models score significantly worse cross-facility than same facility. It's just the domain adaptation model does a lot better of adapting to the environment. And then for deployment, the model needs to be scalable, not just accurate in one data set. And it also reduces the need for labeled target facility retraining. It reduces the need for readjusting that linear regression, that regression that we were talking about with calibrating pumps and sensors, and it supports more consistent quality assessment across processing environments. We ended up getting a processing time of about 12 milliseconds per image, being able to produce over 80 images per second. So really fast processing time and can be integrated. The only caveat is that just setting up production hardware inside of a processing environment and then validating that and then creating some sort of imaging pipeline, setting up cameras, all the barriers that, but the model should be ready. So to summarize what we were talking about is that convolutional neural networks perform better within the training facility than across new facilities. They don't do a good job of adapting. But the unsupervised domain adaptation that we implemented significantly reduces cross-facility prediction error. And the framework that we have is a practical step towards scalable machine vision for food system automation. And for future work, we could include more facilities in the study, we can add more image dates, and we can add a little segmentation model that specifically looks at the longissimus dorsi muscle, which has all the white particles, so that we can zoom in and cut out all of the background information. And then we can also create a heat map that takes the parameters of the model and figures out exactly which pixels it values the most, which would hopefully reflect, which would reflect the marbling, the white fat. And then before I close, just want to talk about some acknowledgments. Thank you for funding from the USDA Agricultural Marketing Service, the University of Arkansas Honors College, my mentor, Dr. Dongyi Wang, my thesis committee, Dr. Terry Howell and Dr. Genghis Koparan, and then the Arkansas High Performance Computing Center. But in the field of, and the main takeaway is that agricultural computer vision must not only work in controlled data, but across field real facilities. because agriculture is not, it's not like civil engineering. You can't just design a bridge to the perfect specifications and then just implement it. Agriculture, living systems, they all change. Every day is a new day. Every environment's a different environment. And that's why this technology can be applied to just much more than just this specific use case. This is the first time it's been used for beef quality, but it can be applied to multiple different aspects of agriculture. And then with that, I'd like to show you some references, and my GitHub repository for the code for this project is also here. And then I would love to open up the floor for questions.